polar T-shape is this. The angles between the chlorine axial, the iodine, and the chlorine axial is less than 180. And between the chlorine axial, the iodine, and the chlorine equatorial, it's less than 90. And that's the only two angles. The rest of these are the lone pairs, right? Okay, we'll stop here, and we'll continue on in the next lesson. All right, let's continue on. We were talking about the category AX6, and the example was sulfur hexafluoride. I want to continue now with a substance that would be considered AX5E. Actually, we've done that one before as a Lewis structure, Xenon Oxxo Tetrafluoride. When we did the Lewis structure for this, we had the xenon with the 4 fluorines attached, and we had the oxygen attached here, and we had 8 electrons around each fluorine. And remember this one, it was 8 for this, plus 6 for this, plus 4 times 7 for this as far as valence electrons go. So we're dealing with 28 plus 14, 42. And we found out that the best Lewis structure looked like this because it had the lowest formal charges. All right, so let's make sure we got 42. 8, 8, 8, and 8 for the fluorines. It's 32. 32 plus 8 on the oxygen is 40, plus those two, the 2 non-bonding electrons on the xenon here makes 42. All right, so the class, we know that the oxygens are more or the fluorines are more electronegative than the xenon, and we know the oxygen is more electronegative than the xenon. So you can either do the arrows pointing towards the fluorines like so, and to the oxygen, or you can do the partially negatives and partially positive on the xenon. All right, so we're ready to continue with this and use VSEPR to come up with the geometry. The classification for this is AX5, AX5E, that's correct. All right, so we use the, I want to stress this part. Your book talks about electron geometry. Electron geometry. The electron geometry is what I have been calling the framework, and that is the electron geometry. If we look at this, it's going to be octahedral. We know, and that's important. That's what we use to decide, which jack we're going to pick up to make our model. So we know the xenon goes here. The oxygen here, maybe the fluorine. If I want to draw a picture of it, I guess I would make a dashed line here, and a triangle here, and a dashed line here, and a triangle here. Let's do a better job on the triangle here. Oops. And then we have a lone pair down here, which I'll make my balloon there. All right. So the electron geometry is octahedral, but the molecular geometry is what we see with the bonding pairs. So the molecular geometry is equal to, or is called, square planar. Square planar. All right, so I'm stressing electron geometry and molecular geometry because I saw some of the quiz questions and they asked for electron geometry, molecular geometry. So electron geometry is what I was calling framework. It's octahedral. The molecular geometry is just based on the non-bonding pair, or the bonding pairs only, And so based on the bonding pairs only, we get a square pyramid here. Here's the base, there's the top of the pyramid here, square pyramidal. Or, yeah, I messed up here. This is square pyramidal, square pyramidal, square pyramidal. All right. These would cancel each other out as far as electronegativity and polar bonds. Nothing's canceling out the oxygen though. There's a small vector this way, very small. This one dominates. The overall resultant vector is in this direction, and so this substance is polar. All right, let's go on. The next molecule would be Xenon Tetrafluoride. Xenon has 8 valence electrons. Fluorine has 7, so we're dealing with a 36 electron system. And you would put the xenon here, and the fluorines like so. And I'm going to use lines. Here's a real quick way to do Lewis structures. Each line represents a pair, right? So right there is 32, and then there's 34, and then there's 36. Remember, the lone pairs, the extra pairs, always go in the central atom. So we know that these are, the fluorines are more electronegative than the xenon. So partially negatives on the fluorines, partially positive on the xenon. So that does it for the Lewis structure. The classification for this would be AX4E2. All right. So the electron geometry for this molecule would be octahedral. Anytime you have 6 things coming off the central atom, there's a total of 6. We have an octahedral electron geometry. So we put xenon here, and the fluorines, well, let's do it this way. The fluorines are going back through the board, and then these fluorines are coming out of the board. And then you have a lone pair above and a lone pair below because they have the most repulsion. They want to be as far away from each other as possible, these non-bonding pairs. So they want them 180 degrees from each other. So this is called, for the molecular geometry, this is called square planar. Square planar. It's the only time we get a square geometry where the angle here is 90 degrees. 90 degrees between each one of the fluorines. So the angle between the fluorine, xenon, fluorine, 90 degrees. Alright, and this substance is nonpolar. There's no resultant dipole moment because these two cancel each other, these two cancel each other out. Alright. So this concludes the different geometries. I guess we could do a summary here. The summary is we have AX2, and that was like the beryllium chloride. We have the category AX3, which is trigonal planar. Just for completeness up here, this is linear. So trigonal planar. Then you had AX2E, which was bent, or also called angular. And that was it for that category. Then we went to AX4. We had AX4, which is tetrahedral. We have AX3E, which was called trigonal. Oops, I'm getting ahead of myself here. Trigonal pyramidal. And then we had AX2E2, which was bent again. The difference between this bent and this one would be less than 120 degrees between the bonding pairs. This one would be less than 109.5. Alright? So the electron geometries of all of these is tetrahedral. Electron geometry. The electron geometry for both of these, the electron geometry, would be trigonal planar. Alright, and then we did the category AX5, which is trigonal bipyramidal. Alright, and then we had the subcategory AX4E, which was seesaw. And then we had AX3E2, which was T-shape. And then the last one in this category was AX2E3, which was linear. And then the last category was AX6, which that's called octahedral. And then we had AX5E, which was square pyramidal or pyramidal. And then we had AX4E, and AX4E2 is called square planar. All right, and that concludes the different geometries that we've worked with. The other part that I expect you to be able to do is if we look at something like between these compounds, that you can tell me which one has the greatest dipole moment. Again, the difference here is 2.1 minus 4.0. This one's 2.1 minus 3.0, and then the other ones you can figure out. But we know that electronegativity decreases as you go down the periodic table. So this one has the greatest dipole moment, then hydrogen chloride, then hydrogen bromide, and hydrogen iodide would be the least. All right. You could also look at it in terms of dipole moments for things like if you were comparing carbon dioxide with H2O with ammonia and let's see, let me think of another one here, carbon tetrachloride, something like that. All right. Well, the carbon dioxide does not have a dipole moment because this is the Lewis structure for it, and it's an AX2, and these pull equal and opposite, and they cancel each other out. So no dipole moment for this. Actually, there's no dipole moment for the carbon tetrachloride because they cancel each other out. So then we're evaluating H2O and NH3, and H2O looks like this with a lone pair coming out here and a lone pair going back through here like that. The electronegativity is 2.1 for hydrogen and 3.5 for oxygen for a difference of 1.4. And so these are being pulled in this direction by the oxygen. Overall, the resultant vector is in this direction. And so let's compare that to ammonia. Ammonia has 3 hydrogens like this. Ammonia is the nitrogen's 3.0, and these are all 2.1. And the difference is 0.9. They're all pointing in this direction. Water would have a greater dipole moment than ammonia, so it would be ammonia and then ultimately water. All right, so that's what you can expect on the quiz, and if you need more help, please let me know. You can email me and I'll be glad to address your concerns.